Welcome everyone. It's another installment of Symmetry in Newcastle. This time our speaker is Hyungryul Baik from KAIST, which is Korean Institute of Advanced Science and Technology, and his talk will be about normal generators for the mapping class group.
All right, thank you very much. Thank you for the invitation, and also thank you all for coming for this talk. It's very sad to give a talk in this seminar only virtually, but still it's very nice to meeting all of you. So today, what I'm going to talk about is the normal generators for the mapping class group. So let me first start with a brief introduction to the mapping class group itself. So throughout the talk, the S will denote a surface, finite type. There's most cases will be just closed, closed, orientable, connected surface of genus, well, at least 2. And the mapping class group of the surface is nothing but you first consider the all homeomorphisms from the surface to itself, which preserve the orientation, and then you consider it up to isotopy. So simply saying is that the set of isotopy classes of orientation preserving homeomorphisms of the surface, and you can check this is a group. So of course this is a group. If you compose 2 homeomorphisms which preserve orientation of the surface, you still get homeomorphisms preserving the orientation. But what you can check is if you change the homeomorphisms you're composing up to isotopy, then the resulting homeomorphism is also determined up to isotopy. So the isotopy classes form a group 2. So this is called the mapping class group. Mapping class group. So one of the theme of geometry group theory is, of course, it's studying groups via nice group action on the space where you understand the geometry of the space. So the space we're going to look at today is so-called curve graph. So I'll denote it by C of S. So this is going to be a curve graph. If you know what the curve complex is, this is just the one skeleton of that complex. If you don't know what it is, that's fine. So we'll define the vertices and edges. So the vertices of this graph are just free homotopy classes. The homotopy classes essential simple closed curves. So here, essential, in the case of a closed surface, just means it's homotopically non-trivial. So sometimes we'll also consider the case when the S has some punctures. In that case, we're also assuming it's non-peripheral in the sense that the curve is not homotopic to a puncture. Okay. So if one of the connected component of the complement of the simple closed curve is either disk or once punctured disk, we call it non-essential. So essential means it's not the case. And we'll ditch vertices of this graph, and the edges of this graph is the disjoint representatives. Disjointly represented curves. So if you have 2 homotopy classes of simple closed curve, if they can be represented, if they can be put in a disjoint position up to free homotopy, then we connect these 2 classes by an edge. And this is how we form a graph out of the homotopy classes of curves. So for instance, if I have a surface of genus 2, maybe this is too simple as genus 3, and say I have a curve, say alpha, maybe this is beta, gamma, and say delta, something like that. So here we have 4 vertices, alpha, beta, gamma, delta, and which vertices are connected by an edge? Well, so here, as you see, alpha and gamma are disjoint, so there should be an edge. Gamma and beta, they intersect, and this intersection cannot be removed up to homotopy. So there's no edge between beta and gamma, alpha and delta as well. Delta and beta should be connected like this. And am I missing something? Is the beta? Oh, beta and alpha is also disjoint. So there are for these 4 vertices, we have these 3 edges. But this is a part of the curve graph. Of course, it has infinitely many vertices, and it's probably slightly non-trivial to show it, but it also has an infinite diameter, as shown in the paper Major and Minsky. So since we have a graph, and so we're gonna make this as a metric space by identifying every edge with a closed interval 0, 1 in a way you like, and then consider the induced path metric that makes the graph as a metric graph. So we'll consider the curve graph as a metric graph. Something you can easily check is the mapping class group act on this graph by isometries. So here by isometries, you can check for the set of vertices to make sure it's actually acting isometrically on the edges as well. That you need to, when you identify each edge with the closed interval 0, 1, you need to do it in a the mapping class group equivariant way. But anyway, so that can be done. So if you think about the simple closed curve, under homeomorphism, it gets mapped to a simple closed curve. So the vertices are mapped to vertices. And then when you have a disjoint curves, homeomorphism would map them to a disjoint curves. So the edges are also mapped to edges. So this is the you have an action of the mapping class group on the curve graph, and then this is an isometric action. Any questions up to here?
I think the graph should be alpha connected with beta. The red graph.
Should be what?
Alpha connected with beta, not alpha with delta.
Oh, alpha connected to beta. Right. That's correct. Is there any edge I actually didn't have? Yeah, I think, yeah, that's right. Thanks. Any other questions? Okay, so we'll move on to the classification of elements of the mapping class group. So here is a so-called Nielsen-Thurston classification of mapping classes. Classification. So for the element of the mapping class group, there are 3 types of element. The one type is called periodic. This is nothing but an element which have the finite order. So the torsion element of the mapping class. So you have finite order. And the second case is reducible. So the reducible case means that there is some disjoint collection of simple closed curves which are preserved under your map up to homotopy. Okay. So here I'm not saying that each curve in this collection is preserved, but the collection itself is preserved up to homotopy. So you may have some several curves which get permuted by the map. And the last type is called pseudo-anosa. So there are many results which it says the third type is generic element of the mapping class group. In particular, in the sense of the random walk in the mapping class group, the work of Joseph Mosher or Igor Rubin shows that there's the asymptotic probability for ending up in a pseudo-anosa element being 1. There are other approaches recently, but I'm not going to go into that direction. So instead of giving a precise definition of what pseudo-NOSF is, we'll give an equivalent condition for mapping class to be pseudo-NOSF using the action of the mapping class group of the curve graph. So to do so, let me introduce the following quantity. So let's say I have some mapping class F, and let's say LC of F is defined to be lim m of the curve graph distance between some vertex alpha and its image under the nth iteration of F, and you divide it by n and then take away infinite and when n goes to infinity. So this is called either stable or asymptotic translation length. So well, the main reason I put lim m instead of lim is just well, mostly because I don't want to argue that why the limit exists. But anyhow, so if you think about this definition, using only by a triangle inequality, this doesn't depend on the choice of alpha. But this is the in the set of vertices of the curve graph. So in some sense, this is measuring on average how much F moves the point in the curve graph in the long term. So what is shown in the paper by Major and Minsky, which is about the geometry of the curve graph. So one of the things they showed there is the mapping class is pseudo-NOSF if and only if the asymptotic translation length is positive. So in the case of periodic or reducible, the asymptotic translation length is 0. And the being positive is actually equivalent for the mapping class to be pseudo-NOSF. So throughout this talk, if you haven't heard of the pseudo-NOSF, this is perfectly good definition for pseudo-NOSF for the purpose of this talk. Any questions? Okay. So one more fun fact about this asymptotic translation length of pseudo-NOSF element in the curve graph. So here is the interesting theorem by Brian Bowditch. So what Bowditch shows is that there is a positive integer which depend on the topology of the surface, such that for every mapping class the surface, the asymptotic translation length is a rational number, and its denominator is bounded uniformly by the constant m. So for a given surface, for a fixed surface, if you look at the length spectrum in the sense of the, you collect all this asymptotic translation lengths of the element in this mapping class group, it's a very, very discrete set. So it's a rational numbers with bounded denominator. So that's one kind of interesting fact. Also, from the definition, we'll use this fact later. So that from the definition, what you can easily check is if you take the power of your element, then the asymptotic translation length is just multiplied by the power. This also directly follows from the definition. Okay, so that's about the asymptotic translation length of each element of the mapping class group for its action on the curve graph. If I consider a subset of the mapping class group, we can consider the minimal minimal asymptotic translation length of the element in this subset. So for this subset, let me define LC of H to be the minimum of the asymptotic translation length of the element in H, which is pseudo-normal, because otherwise the asymptotic translation length is 0 by the theorem of Major-Lewinsky. So we consider only the pseudo-normal element. This question about minimal translation length is so basically, let me first put this question first. So the vaguely put question is, can this quantity, can this distinguish proper normal subgroups of mapping class group from the mapping class group itself? By just looking at the, I mean, in terms of the single element case, by just looking at the asymptotic translation length of a given element, can we say whether the smallest normal subgroup containing the element is whole mapping class group, or it can be contained in some proper normal subgroup? Can we determine this by just looking at the asymptotic translation length? And the reason for this question making any sense is the following theorem, following motivational theorem of Ben Margolid and Justin Lanier. So here is the theorem of Lanier and Margolid. So what they showed in their paper is they gave a bunch of sufficient conditions for a given mapping class to be a normal generator for the mapping class group. So the being normal generator just means the normal subgroup containing, the only normal subgroup containing that element is the mapping class group itself. The smallest normal subgroup containing the element is the whole mapping class group. That's what it means for this element to be a normal generator for the mapping class group. And what they showed is for all genus bigger or equal to 3, and for all element in the for all pseudo-null sub-element in the mapping class group of the surface of genus of 3, if the stretch factor, so if you don't know what it is, you can interpret this as just as asymptotic translation length on the Teichmüller space with respect to the Teichmüller metric, instead of looking at the curve graph. But anyhow, so this is another. So we're going to talk only about the mapping class group action, the curve graph throughout the talk. But there's another space called Teichmüller space, and the people have studied the mapping class group action on there, which is also an isometric action with respect to some nice metric. And this is the translation length in that setting. So in that setting, if the translation length is small, I think the precise number is given in the paper, something like square root of 2. That implies the F is a normal generator, the mapping class group. So what they showed is that if your given mapping class moves point in a only small amount in the Teichmüller space, the translation length is small in the Teichmüller space, then it implies that the given element is actually a normal generator of the mapping class group. So our question here is just asking whether analogous result can be held if we replace Teichmüller space by curve graph. If we look at the mapping class group action on the curve graph, can we say having small translation length still implies the element being normal generator or not? So that's the whole question. And in some sense, there are very tiny bit of partial evidence toward that result. So earlier result of Gaudry and Chai in 2011, and they showed if you look at the minimal translation length of the whole mapping class group for the action on the curve graph. So if we vary G, then this can be considered as a function in G, right? And in that perspective, what they showed is that this is asymptotically 1 over G squared. So this symbol here just means that the ratio between the left-hand side and the right-hand side is uniformly bounded from above and below. Okay, there are some constant, so that this ratio is uniformly bounded from above and below. So this is roughly 1 over G squared. Also, in the paper by Eiko Kin and Hyunshik Shin, what they showed is the minimal translation length of the braid group. So here the braid group can be considered as a mapping class group of n-punctured disk. So there's an analogy here. So if you look at the braid group action on the curve graph of the n-punctured disk, this guy now is considered as a function in n. They showed this is roughly 1 over n squared. Kind of similar, right? So you can just say up to constant, you can just say 1 over all the characteristic of the surface squared. On the other hand, what I shared with Hyunshik later is if you look at the Torelli subgroup of the mapping class group. So here, this is the subgroup of mapping class group consisting of the mapping classes which act trivially on the first homology of the surface. And this is a proper normal subgroup and called Torelli subgroup. So in this case, also by varying G, we consider this side as a function in G. And in this case, it's actually 1 over G. So it's different from the whole mapping class group. The behavior is different. You can actually, if you know what it is, if you can even replace the Torelli subgroup by the first Johnson kernel, but you don't have to worry about it. And so this is a very well-known example of a proper number subgroup of the mapping class group. And in this case, it is distinguished from the whole mapping class group by looking at the minimal translation length. And also, similarly, for the case of braid group, if you look at the pure braid group, which are the element of the braid group fixing the punctures, so in this case, it's 1 over n. Okay, so the list is very short, but there were some examples which might give a hope for the analogous question for the curve graph as some kind of answer. Any questions so far?
Could you just repeat what Bn is?
Oh, the braid group.
So how does that work?
So you can consider this as just the mapping class group of a surface obtained by a closed disk with endpoints removed.
Okay.
And then just, yeah.
Okay, thanks.
The same argument, yeah. I mean, for us, the braid group, we're not going to talk about anything else other than it being a mapping class group of n-punctured disk. That's why, yeah.
Yeah, that's okay.
So also here you assume G greater or equal to 3 in these results?
G should be what? Sorry?
Is in this last result also G greater or equal to 3 or 2 also work?
Oh, so if you think about it, the what happens for final eliminated G doesn't matter because we're only considering the ratio. I mean, so here this means the ratio is bounded from below and above by some constant. So whatever happens for small g, so of course the number is just, there are only finally many ratios, so you can just bound it, right?
Okay, I see. Okay.
Right. Only the tail part is the interesting part. what happens if we get the genus arbitrarily large.
Yes. Yes. Yeah.
Thanks. So for the second half of my talk, we'll consider the more evidence of this sort of kind of question about the mapping class curve action on the curve graph using the viewpoint from the Drury manifold. So let me switch gear and introduce a slightly different notion. It's called the Thurston Norm. Thurston Norm. Let M be a closed Drury manifold. And we first consider its second homology with Z coefficient. Let's just pick one homology class from there. And we'll define its norm as follows. Let me first write and explain what that means. So we'll take some minimum and some prime SIs are the component S prime, where S prime represent the class, and summation at the maximum between 0 and negative Euler characteristic of SI. Okay, so here we first just pick arbitrary representative of this homology class. I mean the arbitrary embedded surface which represent this homology class, which may not be connected. So for each connected component, you measure the Euler characteristic and take the absolute value. And if it is positive, we take it. If it is not positive, then well, we throw it. Sorry, we throw it away, and take a summation of all of them. So this can be done for each representative of the homology class, and you just minimize it over all representatives of the homology class. So that's we're sort of looking for a topologically simplest representative of the given second homology class of the Drury manifold. So here, what one can easily show is here, this, of course, we need the integral homology class to do it, but this linearly extend to H2 with R coefficient. And also, this is only a pseudo norm for arbitrary Drury manifold. What can cause a problem is, of course, if you have essential spheres or essential tori inside Drury manifold, that would give you some non-trivial homology class, which has the zero Thurston norm. But what we will consider is the hyperbolic Drury manifold. So for the rest of the talk, we'll only focus on the case when M is a closed hyperbolic Drury manifold. And in this case, we can assure that this is actually a norm. So this gives you a norm on the second homology of the Drury manifold real coefficient. And what people usually call Thurston norm is it's a dual norm in the first cohomology of Drury manifold using the Poincare duality. And Thurston defined this to develop the notion of fibered faces and fibered cone. So let me briefly introduce what they are. So in the case when M can be obtained as a mapping torus, meaning if you have a surface and then has some orientation preserving homeomorphism, which glue two boundary components together. So here we start from a surface closed interval we have a two boundary component which are homeomorphic. You just pick whatever homeomorphism you like, and you glue two boundary components together, and you get a closed tree manifold. And this is simple mapping torus. We'll denote it by M sub F. So naturally, this tree manifold fibers over the circle, where the fibers are just homeomorphic copies of the surfaces, and the monodromy of this fibration is your map F. Okay. So in this case, the this map from the fibration map M from S1 will give you some first cohomology class of M. So the question Thurston asked is which primitive cohomology classes of tree manifold M, if we a priori know M can be represented as a mapping torus, which primitive cohomology classes correspond to fiberations over the circle. And what he showed is kind of very interesting. So first of all, the Thurston Norm ball, the unit norm ball for Thurston Norm is a rational polytope. And if you look at one of the top dimensional face, let's call it F, because this is some top dimensional face of this unit norm ball. Say this is the origin, and consider the cone over F. If we happen to know some primitive cohomology class inside, primitive integral cohomology class inside of this cone, do correspond to a fibration of this tree manifold over the circle, that we actually do know that all primitive integral cohomology classes in the cone correspond to different fiberations of this same tree manifold over the circle. So in particular, what this says, if you never thought about this, in particular what this says is if you have a tree manifold which fibers over the circle, it usually fibers over the circle in infinitely many different ways. Not just that one, but in many different ways. And once you have a one cohomology class which correspond to the a fibration of the tree manifold over the circle, then all other cohomology classes inside the cone, the same cone over some top dimensional face of a unit norm ball for the Thurston Norm, do correspond to fiberations of the tree manifold over the circle. So here, in this case, F is called a fibered cone, and C is called, oh sorry, this is fibered face, and C is called fibered cone. The only thing which matters for this purpose of this talk is, well, there is some sort of cone we can consider inside of the cohomology of tree manifold, where all the primitive cohomology classes give you a way to understand this tree manifold as a mapping torus. And each of these primitive cohomology class inside the cone do correspond to a, say this is a class alpha, then there is a pair as alpha and psi alpha. So this is the fiber, and this is a monodromy. It just says that you can obtain tree manifold M you're looking at from S alpha towards closed interval by gluing two boundaries by this map psi alpha. There are infinitely many different ways to express the same tree manifold in this manner, and they are sort of encoded as a primitive cohomology classes in this cone. That's all we need. Okay. So here there are infinitely many different ways to express the tree manifold in terms of this pair, surface, and how to glue. And here is here's a theorem. This is the joint work with Eiko Kin, Hyunshik, Shin, and Chenxi Wu. So first of all, there is a constant C such that for all alpha in the fibered phase, so we should start from some fibered Riemann-manifold M, also some fibered phase F. Then there is some constant which depend on the fibered phase you choose, such that for all primitive cohomology classes inside the fibered cone, the asymptotic translation length of the monodromy corresponding to that guy is bounded from above by C over the Euler characteristic of the fiber. So in some sense, relatively small translation length. So if you recall the theorem of Lonnie and Margalit I mentioned before, they showed something about if the translation length on the ti-cumulus space is small, here the small means smaller than fixed number, then it should normally generate the whole mapping class group. So in the curve graph, actually the same type of statement cannot hold, but the hope is maybe here small should mean by constant, not just smaller than some fixed constant, but constant over the genus of the surface. So some normalization should be needed. And then that here, this is what exactly what that is, right? So C over the, roughly just the genus of the surface. And so this is the first part. And interestingly, what we can also say is that for all but finitely many alpha in CF, the psi alpha actually normally generate the mapping class. So sort of morally support the idea of having a small translation length implies the normal generator for the mapping class group. Except here the caveat is we only know this fact for some two-dimensional slice, two-dimensional rational subspace. So the conjecture is, of course, this statement holds for the whole fibered cone. But what we know so far is if we have a two-dimensional slice of the fibered cone, in that slice, we can throw away only finitely many. And then for all of the other primitive classes, the monodromy normally generate the mapping class group of the fiber. The reason I cannot remove this part is because how much we have to throw away for each slice is not controlled if you change the slice. So at this point, our argument doesn't go through the whole fibered cone, but I'm hoping that it's actually true for the whole fibered cone. Any questions up to here?
Yeah, maybe I would like to ask, so if I understand it correctly, like, depending on the slice, how many finitely many depends on the slice. Is that correct? And is there some kind of measure of complexity, like that links the slice to how many?
That's excellent question. I don't know. So I'll actually give you the idea of the proof for the rest of the talk. You'll see why I don't.
Okay, thank you.
Other questions? Okay, so I'll give you some important point in the proof. So the one key ingredient is the following lemma, which actually does appear in Lania Margolid, but it's also a simple fact you can extract from, for instance, the primary mapping class group book by Farb and Margolid. So it's just a combination of a well-known fact about the mapping class group. But let me first state it. So let F be an element in the mapping class group, genus of list 3. And suppose there is non-separating simple closed curve C on the surface such that the intersection number between C and F of C is 0, and the homology classes of C and F of C are different. They are not homologous in the surface. Then the F is a normal generator of the mapping class group. So here, let me explain the terminologies here. So the non-separating just means it doesn't disconnect to the surface after you remove the surface. So if you have a surface like this, this is the example of a separating curve, but this is an example of a non-separating curve. And the intersection number is just a minimum intersection, the cardinality of the minimal intersection between C and F of C up to homotopy. So this just means that C and F of C up to homotopy, you can put them disjointly, yeah? And they're not homologous. If you know these conditions for some curve C, then F is a normal generator of the mapping class group. So here is the proof sketch. So the genus being a list 3 is being used from the very beginning of the proof. So if the genus is a list 3, we can find the following subsurface inside of your surface, which looks like 4 punctured sphere, where the rest of the surface is somewhere there. If genus is 3, then they should be simply just connected. But if the genus is larger than 3, there's some more complications. And here the curves are A, B, say C, D. Here C is the C in the statement. And say there is a curve X, another curve Y, and another curve F of C. So here the configuration can be done so that none of these two curves are homotopic or homologous, and just put them in this way. Each of them is non-separating, and any two is non-homologous. Okay? You can arrange them that way if you know genus is a list 3. So once you know that, then now you're just running the argument using some fact you know about the mapping class. So the most famous relation in the mapping class group is the so-called the lantern relation, which it says in this configuration, the T, TV, TC, TD is T of C, TX, and TY. So here, T sub some curve means then twist. So if you don't know what it is, here you have a curve, simple closed curve. You cut the surface along the curve and twist one side 360 degrees and glue the surface back together. So this is some homeomorphism of the surface, which is supported in a small neighborhood of your curve. The effect of that homeomorphism is if you have some curve passing through the curve you're then twisting along, then maybe originally the curve goes just simply like this, but then after then twist, that should wrap around the curve once and then pass. Okay, so that's what is called the then twist. So the then twist along curves A, B, C, D, and this is a composition, and the order doesn't matter because if you think about this, the then twist along two disjoint curves should commute because this is a homeomorphism when it's support in a small neighborhood of a curve. And here there's a then twist along f of c and x and y, and here the cyclic order matters. Okay, but anyhow, so once you arrange like this, then using the fact that the then twist along disjoint curves can commute, you can rewrite thing like a TD is TC inverse TF of C, TA inverse TB, TB inverse TY by moving the then twist along ABC to the right hand side and then arrange a little bit. So this guy, for instance, if you look at this guy, so this is same as TC inverse composed with F, TC, F inverse. So the then twisting along the curve f of c is same thing as first you're mapping f of c to c on using f inverse, and then do then twist along c, and then move back to f of c by f. So then twist along f of c is same as conjugation of then twist along c by f. So we can rewrite this guy as this guy. So that's what I mean. And once you do that, then, well, then this is just by regrouping TC inverse F TC composed with F inverse. Now this is a conjugation of F, conjugate of F. So it should be an element of the normal closure of F. If you look at the smallest normal subgroup containing F, this should be in there. Well, F inverse should be in there. So the whole thing should be in the normal closure of F. So TD is a composition of this and this and this. So the first one we showed, it is an element of the normal closure of F. And second and third can be also using a similar trick. We can do this. So C and F of C is a pair of disjoint simple closed curves which are not homologous, and A and B is also those pair of disjoint simple closed curves which are not homologous by the arrangement of the curves at the beginning of the proof. So there should be some homeomorphism of the surface which maps this pair to this pair. Just using the classification of the surface after topology. So by using this homeomorphism, you can do this trick again. So if, let's say C is mapped to A under F, H, that means A is just H of C, so T sub A can be expressed as a conjugate of T sub C conjugate by H. So, and using this, you can write to show that actually the TA inverse TB is also element of the normal closure of F. I'm skipping some details, but this can be just written down explicitly. And by exactly same reason, the third one is also an element in the normal closure of F. So what this shows is that the TD, the then twist along the curve D, is an element of the normal closure of F. And now, if you have any other non-separating curve on the surface, again, there should be some homeomorphism which maps D to that non-separating simple closed curve. So this actually shows that all non-separating then twists are element of the normal closure of F because they're conjugate to each other. And now there's a famous fact that the whole mapping class group actually is generated by the non-separating then twist, the then twist along the non-separating curves. So since we just to show that the generators are element of the normal closure of F, the whole mapping class group should coincide with the normal closure of F. So that's the sketch of the proof. So basically, the simple criterion for having this curve will guarantee that this mapping class is a normal generator of the mapping class group. Now, using this, you can do something in the fibered cone. So let me go back to the picture of the fibered cone. So suppose I pick this time two primitive classes, alpha and beta. Alpha correspond to some fibration, so fiber S alpha and monodromy psi alpha, and beta also correspond to some fibrations. So there's some fiber S beta with monodromy psi beta. So now what we're gonna look at is the sequence obtained by alpha plus n beta. This gives you a sequence of primitive cohomology classes in the fibered cone. And this we can control. The control here means using the theory of Freed. So if you, so I'll not go into too much details, but instead I'll give you some useful fact. So here's what Freed studied in 80s. So consider the mapping torus before gluing. So here is your, say in this case, for instance, here is your S alpha cross 0, 1. And this can be foliated by following line segment, which is just a point cross the interval 0, 1, right? For each point in the surface, that point cross 0, 1 will give you some line segment from one boundary to other boundary, right? So you have this this three manifold with two boundary component obtained as a union of all these line segments. And now you glue them together using the homeomorphism psi alpha. So this line segment will now continue, right? So X goes to psi alpha of X, and psi alpha of X goes to psi alpha of X, etc. So it actually continues. So this will define a flow inside of your closed three manifold. And then because this forming a mapping torus was originally called taking a suspension, so this flow is called a suspension flow. What's interesting is the Freed showed that the suspension flow is actually fibered cone invariant. So you have a same three manifold which fibers over the circle two different ways. So that means maybe you have two fibers and two monodromies, and then maybe the fibers doesn't have to have the same genus, right? So you do have here the way of expressing the same string manifold using surface of genus 2 and glue somehow. Here the other way you have a genus 5 and glue somehow, and it's the same string manifold up to homeomorphism. And you do have a suspension flow. But what Freed shows is that suspension flow is if these two fibrations, if the two cohomology classes corresponding to these fibrations are in the same fibered cone, then there must be a homeomorphism from M to itself, which preserves this flow. So the suspension flow should look the same. even though you form it in a completely different way. So up to homeomorphism, if they are the same flow, then if you think about this, well, this in both cases, the fibers, the surface fibers, is an embedded surface in the three manifold, which is transverse to the flow lines. And very surprisingly, what Fried showed is that, well, that's actually an if and only if condition. So if you can find, so here the suspension flow is a fibered cone invariant. So you are given a flow, and if you pick arbitrary embedded surface in the three manifold, which is transverse to the flow line of the suspension flow, then actually this is a fiber of the fiberation. And the first return map along the suspension flow is the monodromy, and that gives you fiberation in that fibered cone. The suspension flow is very useful tool to find different fibers at the same trim out. Does it make some sense?
More or less.
Yeah, I know this is if this is something you haven't thought about, it's very difficult stuff. But the point is, once you know this, then sort of pictorially, this is what happens. So let's say this is S beta. So recall we're looking at two cohomology classes, alpha and beta, and we are considering the sequence obtained from alpha plus n beta. And here is the surface S beta. And well, we're multiplying n to beta, so we actually do want the n copies and parallel copies of S beta. And there is some way the S alpha is also located. And let's assume they are put in the minimal position. And here we have a suspension flow. Suspension flow. So the point is, how do we find a surface corresponding to this class, alpha plus n beta, from S alpha and S beta? Well, so here the S alpha is surface representing the homology class due to the class alpha. Alpha is a first homology class, so it's due to some second homology class. So there is some embedded connected representative S alpha, which means actually it's not just the surface, it actually comes with an orientation, right? So S alpha with one orientation correspond to alpha, and the different opposite orientation will correspond to negative alpha. So S alpha is an oriented surface, not just a surface. So here, as let's say this is a part of S alpha with orientation, and say this is S beta with orientation at the intersection, where intersection is actually a curve. You cut them along this curve and glue them in the way that like this. It's called the surgery. So the resulting surface still has a well-defined orientation, but now the one end of S alpha is connected to one end of S beta, and the other end of S alpha is connected to other end of S beta. So this way, if you have a S betas and S alphas, and then you do the surgery at every intersection curves, so you get a surface which we call as sub alpha plus n beta, corresponding to the class alpha plus n beta. And this is now new surface, which is transverse to the suspension flow. So if I take a curve here like this, and the pictorially suspension flow will map this curve to the next level. So here you have this transverse flow. And because we started from n parallel copies of S beta, which are staying very close together, so if you pick a curve on the one copy of S beta, then the suspension flow will move this curve to a next copy of S beta. And then if you apply it again, then go to one level up and one level up, etc. And what we can show is that, well, if this curve is C, and if this is psi alpha plus n beta of C, by Fried theorem, this is the first return map is the monodromy of the new fibration, right? So they are disjoint simple closed curves. And once n is large enough, then you can show combinatorially they are not homologous. So to check non-homologous part, you need some room. That's why n should be large. So that's where we need n large enough here. In this case, if n is large enough, then you can show that the C and its image are non-homologous. Now, using the lemma we proved, and then this monodromy normally generates a mapping class group. That's for this one particular sequence, right? And what we can show is really just the last sentence. So in this fibered cone, you can first consider it translate using a vector pointing inward of the fibered cone. And here, if you push it far enough inside, then the stretch factors of the monodromy can be arbitrarily close to 1 using Macmillan's theorem. So inside there, using the theorem of Blany and Margolid, they all have a small stretch factor, so they are all normally generate. And outside of the translated cone, you can express them as a union of finitely many such sequences. So each sequence, you have finitely many exceptions, and you have finitely many sequences, so you throw away only finitely many. So that's how you obtain the result for the all but finitely many primitive cohomology classes that monodromy normally generate. Here, the last bit was can be done assuming it's two-dimensional. Okay, let me stop here. I'm running out of time.
Okay, thanks to our speaker. I think that was a really nice talk. Do we have any questions for Harry? Well, if not, let's thank Harry again.
Thank you.
And let's reconvene in 30 minutes.